Hello, everyone, and welcome back to the channel. Today, we are diving into a fascinating and incredibly powerful concept in system design database, which is multi-master replication. You have probably heard of or even implement the traditional primary replica setup. That's where one server, which is the primary one, handles all write operations and then replicates those changes to one or more read-only replicas. It's fantastic for read-heavy workloads, but what happens when your write traffic explodes, or when you need low latency writes across continents? Relying on a single primary can quickly become a bottleneck, and or maybe a single point of failure as well. I would say, and also could introduce some sort of unacceptable latency for distant users. So today we will talk about multi-master replication, because actually this where multi-master replication steps in fundamentally and solve all of these problems for us. Okay, so what is it? So we need to break down what multi-master replication truly means. Imagine, okay, let's go with the read replication that we always know, that we have like a secondary server, I call it S1 and S2, and we have a master, let's call it this M1, and the master serve all the write operations, and it will replicate the data across the replicas. Okay, so again, multi-master replication, we need to understand what it truly means. Imagine a traditional primary replica, as you can see here. But now, instead of just one node being able to write, you have several nodes. Each one is capable of independently receiving and processing write requests. Each of these nodes acts as both a master for its own writes, and also can act as a replica for the write originated from other masters. So we have another master here, which call it master 2. Let's go, we have another server here, or another secondary, or another replica, which will be 3, here 4, and it replicates the data across these servers, and it will replicate across this master, and the master also will replicate this data across the other master. So let's understand the core concept. When an application connects to one of these master nodes and issues an insert, update, or delete command, that node process the write locally. Immediately after it, or near immediately, that change is then asynchronously or semi-synchronously replicated to all other master nodes in the cluster. This ensures that eventually all nodes hold the same consistent set of data. This writes everywhere paradigm fundamentally changes how you think about database architecture. You are no longer bottlenecked by the capacity of a single machine or the network latency to one center point. Instead, your write workload is distributed across multiple active applications in your database cluster. This is in stark contrast to read replication, when only one database can handle writes and others are purely for reads. With multi-master, every participant in the cluster has the potential to handle both read and writes operation, leading to a much more dynamic and resilient system. Okay, why to choose this system? There are multiple reasons, but we will focus right now only on 3. First, we have low latency writes for globally distributed applications. This is perhaps the most compelling reason. Consider a social media platform or an e-commerce site with users located all around the world, in North America, Europe, Asia, and so on and so forth. In a single primary setup, a user in say, for example, like in Munich, Germany, would have to send the write requests like posting an update or placing an order, all the way to the primary database potentially located in let's say that in the USA, in Washington or something like that. This round trip could introduce hundreds of milliseconds of latency. With multi-master replication, you can strategically place master nodes closer to your user bases, one in North America, one in Europe, and one in Asia. Now, the Sydney user writes to the master in Asia, experiencing much. Not Sydney. Sorry, the Munich user writes the Munich user writes to the master. It's basically experiencing much lower latency because we put the a replica in Europe closer to the user in Munich. Munich is in Germany. And yeah, all these regional masters then asynchronously replicate changes to each other, ensuring global consistency over time. This drastically improves the user experience by providing localized with performance. Number two, we enhanced high availability. In traditional primary replica setup, if the primary database fails, you have to go through a failover process where a replica is promoted to become the new primary. This process, even if automated, can involve a brief period of downtime or service interruption. With multi-master application, if one master node fails, the other active masters can seamlessly continue to handle both reads and writes. The system inherently has more redundancy and no single point of failure for write operations, ensuring the system stays operational even if one database node fails. Number three, we have distributing high write traffic. If your application generates an incredibly high volume of write requests that a single database server simply cannot handle, multi-master replication provides a way to horizontally scale your write capacity. Each master node can absorb a portion of the write load, effectively distributing the strain across multiple servers. This is particularly useful for applications with a balanced read and write ratio, or even write-heavy workloads that push the limits of individual server performance. Okay, we need to talk about the major challenge which is a data conflict. What is a data conflict? Okay, we said that we have two masters, like master one, we have master two, and we have, like, let's say the slaves, or let's call them secondary, or whatever it's best for you. So a data conflict occurs when two or more master nodes concurrently try to update the same piece of data before their changes have even replicated to each other. For instance, imagine a user profile record where node A updates the user's email address at the same time node B updates the user's phone number. Or even more problematic, both of them will try to update the same field, which is the user email, to different values. When these changes eventually arrive at common node, the database has to decide which change is the correct one. If not handled properly, this can lead to inconsistencies and data loss. Okay, how to solve that? Let's try to understand strategies to handle conflict resolution. The first one, which is last write wins. This is often the simplest and default approach in some systems. As the name suggests, the change that arrived last at a given node wins. This is easy to implement, but can lead to non-dramatic behavior and potentially data loss if the last write wasn't intended right. For example, if a user updates their profile on a node A, and then immediately on node B, the update from node B might override the one from node A, even if node's A update was logically newer based on user's intent. Number two, we have user-defined logic. This is often the most robust, but also the most complex. The application developers define specific rules or functions to merge or resolve conflicts. For example, if two nodes update a shopping cart, the resolution logic might involve merging the items from both updates rather than simply overwriting one. This requires a deep understanding of your business logic. Number three, we have a timestamp based resolution. Each write operation here is tagged with a timestamp. When a conflict occurs, the system accepts the write with the most recent timestamp. This is an improvement over the last write wins, but still doesn't generate the correct outcome if clocks are not perfectly synchronized across distributed systems. Next, we have vision vectors. This is more sophisticated technique that tracks the version or it takes the version of data across multiple nodes. When a conflict is detected, the version vectors can help identify which changes are truly concurrent and allow for more intelligent merging or flagging for manual resolution. And lastly, we have a conflict avoidance. Sometimes the best strategy is to design your application in a way that minimize the chances of conflict in the first place. For example, by partitioning data logically so that specific data types or user segments are always written to only one master, even if it's multi-master setup. Okay, we could talk about some even more trade-offs about multi-master database. The first thing, which is increased system complexity, because this is not a setup for the faint of heart for or for simple applications. Managing multiple databases that are constantly replicating changes to each other is inherently more complex than managing a single primary with read replicas. You will need robust monitoring, advanced tooling for deployment and maintenance, and a deeper understanding of distributed systems. Troubleshooting issues in a multi-master environment can be significantly more challenging. Number two, we have higher latency for strict consistency. While multi-master helps with low latency writes to the closest node, ensuring strong consistency, ensuring strong immediate consistency across all nodes can actually introduce higher overall write latency. If you require every single write to be instantly consistent across the entire cluster, the replication process has to be synchronous or nil synchronous, meaning the originating node has to wait for confirmation for other nodes before acknowledge the write. This can lead to delays. And number three, we have write amplification. This is a key performance considerations. Like every single write operation intended on any master node needs to be replicated to all the other master nodes in the cluster. This means a single logical write a single logical write request from your application turns into multiple physical write operation across your network and disk. This amplification of writes can significantly increase network loads and disk I/O, impacting the overall performance and potentially increasing infrastructure costs. And lastly, we have operational overhead and costs as well, because with more moving parts and increased complexity, you will naturally incur a higher operational overhead. This translates to more demanding monitoring, potentially more specialized stuff, and higher infrastructure cost for running multiple powerful database instances. Okay, to our conclusion. So to summarize this, multi-master replication is a powerful and sophisticated database scaling technique. It truly shines for globally distributed application that require low write latency across different regions, and for systems where maximum availability for write operation is paramount. It allows to distribute your write load across multiple servers, going beyond the limitation of a single primary. Of a single primary master. However, if it's not a silver bullet to inherit the challenges of managing data conflicts, the increased system complexity, and the phenomenon of right implication, means it's a solution that requires careful design. Also, robust implementation and strong operation enterprise. So that's it for this video. And if you like this video, make sure to like, subscribe, and hit the notification bell so you never miss any video. And see you guys in future videos.